Students, I am Dr. Krishna Kingkar Pathak, Department of Physics, Arjobidabit College. Today I have chosen the topic Statistical Mechanics because maximum of you have the complaint that the subject is confusing and you do not get any confidence after studying it. Regarding this, I must say that recently I have gone through a book. In the introduction part, it is written that Boltzmann, who has been carried maximum of his work, died in 1906 in his own hand. Similarly, Paul Unfresh also carrying the same work died in the same way in 1933. So the thing is quite natural. You need not to worry about all these things. But whenever there is a confusion, then we have to go by the mapping technique. In mapping technique, we first summarize the thing which we are going to derive in pen and paper, and that will remove your confusion, of course. So statistical mechanics is broadly divided into two parts. One is classical statistics, another is quantum statistics. The main difference which we are using here is that classical statistics deals with the distinguishable particle and quantum statistics deals with the indistinguishable particle. Again, quantum statistics is divided into two parts. One is your Bose-Einstein statistics, another is your Fermi-Dirac statistics. In Fermi-Dirac statistics, Pauli's exclusion principle can be applied. In Bose-Einstein statistics, this Pauli's exclusion principle cannot be applied. Okay, so regarding application part, here in classical statistics, it has been applied to the ideal gas equation like your RMS, root mean square speed, average speed, all these things are there. In Bose-Einstein statistics, mainly we study the radiation pressure, Planck's law, means displacement law, Bose-Einstein condensation. And in Fermi-Dirac statistics, we mainly study the degenerate pressure, free electrons in metal, and the white dwarf, the stability of white dwarf. Those are studied in Fermi-Dirac statistics. But the main thing among these three is that we have to first find out the distribution law, Maxwell Boltzmann distribution law, Fermi-Dirac distribution law, Bose-Einstein distribution law. And this distribution law is dependent upon the probability. So we have to first find out the probability for these three individual conditions, laws. In deriving these laws, first we have to find out which are the common points. The common points is, first we will find out the equilibrium condition. Equilibrium condition, so that your probability is constant. I will consider in log, and if it is constant, then its differentiation will be 0. This point is common for Maxwell Boltzmann statistics, Bose-Einstein statistics, as well as Fermi-Dirac statistics. The second point, I will consider that the total number of particles in the system will remain constant, so that the differentiation of that quantity is also again 0, because the number of particles is constant. No creation, no destruction of particles will be considered there. Then what we will consider, there is no external interaction. There is no interaction, so that your energy and this term, multiplication of this term, will be equal to 0. So here what I will do, I will multiply by a Lagrange multiplier here. As you know that this Lagrange multiplier is used in partial differential equation, and here I will use another Lagrange multiplier like this. Okay, these three equations will be common to both these Maxwell Boltzmann statistics, Bose-Einstein statistics, and Fermi-Dirac statistics. I will use these things. Okay, now the question is, we have to find out this probability. Again, this is probability. Sometimes I write P or W, it doesn't matter, but this probability we have to find out. For finding out this probability, let us move towards the microstate and macrostate. I have made the table already so that it will save the time. So micro means small, as you know that, and macro is your larger quantity. Suppose you consider 4 particles which are distinguishable, A, B, C, D. We are considering 4 particles, and there are 2 compartments. We have to arrange it. Okay, so how this will be arranged, let us say for the first time A, B, C, D. I am writing here small letter, doesn't matter. This is capital letter, this is small letter. So this is A, B, C, D. This is 0. This is the first one. Then what I can do? I can do here B, C, D, here A. Then A, C, D, here B. Then of course you will get A, B, D. Then here C. Then you will get A, B, C. This is D. Or another way we can arrange it 2 by 2. A, B, C, D. A, C, B, D. A, D. B, C. B, C, A, D. Okay, then BDAC, and you can write also CD and AB. No alternate arrangement is there. Okay, so here you have 4 arrangement and here you have 6 arrangement is there. Okay, this arrangement and then the alternate one also there, A, B, C, D. A, B, C, D. Then of course this reverse it, B, C, D. Then A, C, D, A, B, D and A, B, C. Okay, and you reverse it, A, B, C, D. This is 0. So you have 4 particles and you have 5 arrangement, 1, 2, 3, 4, 5. So this is 4 plus 1, that is we call n plus 1 arrangement is there. Now look at this Dirac arrangement. What is there? This is 4 and 0 only. Okay, and then here what we have used, 3 and 1. Then what we have used, 2 particles in it. Then you have used 1 and 3. Then you have used 0 and 4. So here you see in macrostate what we have considered only that there are 4 particles there and 0 is here, 3 particles here, 1 is here. But in microstates what we have to know? We have to know how these 3 particles are arranged, either BCD, ACD, ABD or ABC or something like extra here. Say in 2 by 2 how these are arranged, that is understood in microstates. But in macrostates it is sufficient 2 and 2. In one chamber there is 2, in one compartment there is 2, and in the another there is 2. So this 2 and 2 is sufficient for us to understand the macrostates. But in microstates we have to know whether AB is there or CD is there. Okay, so in general we to understand the properties we always use the macrostates. Now look at the frequency of this. Here this is only 1. Then you have 4 arrangement. Then you have 6 arrangement here. And then you have 4 arrangement. Then you have 1. So total is how much? 4, 5, 11, 15, 16. So total is our 16. This part will give us the probability. This 16 will give us the probability. Okay, so here what you see that there are 2 to the power 4, compartment is 2, particle is 4, 2 to the power 4, 16 arrangement is there, or frequency is 16. So we will use this, or we will extend this part towards the Maxwell Boltzmann statistics, Bose Einstein statistics and Fermi Dirac statistics. Then let us consider say a smaller system for n number of particle 2 and for chamber 2 suppose. Okay, so what was the basic difference between these and these? This is distinguishable and these are indistinguishable. So here what we consider, these are distinguishable, A, B, C, D. But if I consider in quantum states or in Bose-Einstein statistics and Fermi-Dirac statistics, then I have to consider A or B, because these are indistinguishable. So those points we have to consider here. So suppose now you have two particles and two chambers. So let us move how to arrange it. Say I am considering here two chamber A, B. Okay, then I can arrange it, just reverse it, BA. Okay, then what I can consider? I can consider the two particles here in the same compartment, BA, and I can consider the another arrangement, AB. So there are only four arrangements here. Okay, but in Bose-Einstein statistics, since these particles are indistinguishable, so suppose I consider those are simply AA, I can do this, then I can do this, 0, and then of course I can place A0 here. Okay, this is 0, nothing else. So there are three arrangements here. So mind it, here you have placed two particles in a single step because no Pauli's exclusion is obeyed here. So you can put 2, 3, 4, 5 in a single chamber, in a single compartment, no problem. But in Fermi Dirac statistics, you cannot do that. You have to place only one particle in one compartment. So there is only one possibility. So this is your one possibility. So there are four possibilities, there are three possibilities, and there are one possibility here. Okay, so let us put this. So this chamber we write as Gi, the number of particles we write as Ni. So if I write it, this 4 can be written as Gi to the power Ni. Okay, so this is called equal a priori probability. This part is called equal a priori probability. Okay, and here these three I can write in a more comfortable way. Say 2 plus 2 minus 1 factorial divided by 2 factorial and 2 minus 1 factorial. Okay, you see the same result, you will get 3. 4 minus 1, this is 2, this is 2 minus 1 is 1, so you will get 3. Okay, so what I can write in terms of Ni and Gi, I can write it, say probability is equal to this 2 Ni plus Gi minus 1 factorial and then Ni factorial Gi minus 1 factorial. Okay, so this same thing I am writing in a different way. Here also I can write, say this is 1, we arrange it in a comfortable way, factorial 2 and 2 minus 2 factorial, same thing, factorial 2 will be cancelled out, 0 is 1, so ultimately this will be 1. So I can write it again like this, Gi factorial, Ni factorial and Gi minus Ni factorial. Okay, so here you see, but one thing is there, in case of classical statistics or Maxwell Boltzmann statistics, we have to consider that permutation and combination. You have understood those combination theory, that if you are to combine n different objects taking r at a time, then what you write? You write NCR is equal to factorial n factorial r n minus r, right? Okay, here I have considered one is your equal a priori probability, and we have to consider another probability which is called thermodynamic probability here. That thermodynamic probability is W is equal to, suppose first I place n1 particle, then for NCR, using NCR I will get total number of particles is this, and then n1 is there, in R you will get n1 factorial and then n minus n1 factorial. Okay, this will be your W1. Then for total we will write, first you arrange n1, then you arrange for n2. n2 means n minus n1, the remaining part is n minus n1 factorial, then it is n2 factorial, then it is n minus n2 factorial, and so on. So this is called our thermodynamic probability, which gives us for n1 different objects you will get this, for n minus n1 or n2 different objects you will get this, and the total probability is always multiplied. That's why you are getting this W is equal to this. So this is called thermodynamic probability. Now the total probability is again multiplied, so total probability is Z into W. So I will get this part will be always cancelled out, this part will be cancelled out, so I will get only factorial n for this part, W part. I will get factorial n by n1 factorial, n2 factorial, n3 factorial, and so on for this W part. And for Z part already you have Gi to the power ni. Okay, so this part, in case of summation you write this symbol, but in case of multiplication you write this symbol pi. Okay, so I will write it factorial and I will bring it outside, then pi I is equal to 1 to k, say there are kth cell, then 1 by ni. Okay, and then Gi to the power ni. So this is the probability for Maxwell Boltzmann statistics, and this is the probability for Bose Einstein statistics, and this is the probability for Fermi Dirac statistics. Okay, so here as we have considered a number of cells or number of compartment that is ranging from I is equal to 1 to k, here also I will write for I is equal to 1 to k, pi is equal to 1 to k, I will write ni plus Gi minus 1 factorial, then ni factorial, and Gi minus 1 factorial. Similarly here also I will consider for all the chambers, pi I is equal to 1 to k, Gi factorial, ni factorial, and Gi minus ni factorial. Okay, so we have calculated the probability. As I told you that these were the basic ingredients to derive this distribution law. Okay, so we have got these probabilities. Now your one question will arise: why this probability is there, that means thermodynamic probability is there, but not here and here? Because you see, this thermodynamic probability is coming from where? Combination of n different objects taking r at a time, that gives you NCR. Different objects, but here this is not different, this is identical and indistinguishable. So this part, this combination part will not come here because they are indistinguishable. These are distinguishable, that's why this part is coming. Clear? So we are getting these three probabilities. Okay, let us then derive the basic distribution laws. Okay, so I have already written here, these are the probabilities: P for Maxwell Boltzmann statistics, for Bose Einstein statistics, and for this. Okay, so to deal with all this, let us first take logarithmic on both sides. Log of P is equal to log of n factorial. This pi will become summation because log of a into b is equal to log of a plus b, log a plus log b. That's why this pi will become the summation. So I will use the summation I is equal to 1 to k. Okay, log of Gi to the power ni. This is minus summation ln ni factorial. Okay, note this Gi part will be considered as constant, this n total number of particles will be constant. So when I will differentiate, remind it, when I will differentiate it, this part will be 0. Okay, then same thing I will do here. Ln P is equal to summation, okay, ln ni plus Gi minus 1 factorial minus this summation ln ni factorial minus, again I am just expanding it, log a into log b is equal to log a plus b, minus sign is already there, so gi minus 1 factorial. Same thing I will do here, ln p, ln summation ln gi factorial minus summation ln ni factorial minus summation ln gi minus ni factorial. Okay, so this is, we have taken the log on both sides. Now you see the main problem is with our this factorial sign. You cannot deal with this factorial sign, whatever it is. You cannot, you have never seen a differentiation formula dealing with this factorial sign. So what I will do, we have to use one approximation to remove this factorial sign, because what I require this d ln p is equal to 0. First I require this. So for this part I have to differentiate this probability. So to differentiate this probability I have to remove this factorial sign. For that purpose we have to go by Starling approximation. What this approximation says, Starling approximation says that if you have any number factorial is there, then you can write it n ln n minus n. Ln n factorial can be written as n ln n minus n. So I will use here simply ln p is equal to n ln n minus n minus summation, here no factorial is there, so this power will come in front of this ln, so ni ln gi, and this again you have to use the Starling approximation, minus summation ni ln ni minus summation of ni, this ni ln ni minus summation of ni. Again summation of ni is nothing but total number of particles, so this will be cancelled out. Okay, so the remaining part is n ln n minus summation of ni. I will take common so that ln ni by gi. You can write this part is front, so I will write ni by gi. Okay, here I have missed one sign, that is this one, plus sign is there, because this minus ni ln ni and this minus will be plus, and here this is coming from this plus sign, that's why this will be plus only. Okay, then what we have to find out? We have to find out this differentiation of this. Let us first find out this differentiation of this. So d ln p, this part will be constant because ni, as I told you, this is constant, so this part will be simply 0. Then for this part, first function into second function, so first differentiate it, minus summation of dni, leave it ln ni by gi, then differentiate the second part, so leave the first part as it is, ni, differentiation of ln ni by gi. Okay, so this is log of x part. Again I have to log ni minus log gi, but this gi is constant, so differentiation of log gi will be 0, so I will directly put it equal to 0. So this part will be simply minus summation of dni ln ni by gi minus summation ni ln ni, differentiation of log of x is equal to 1 by x dx, so 1 by ni dni and minus this part is equal to 0. This log of gi d ln gi is equal to 0. I will not write that part. So ni will be cancelled out. Ultimately summation of dni. So this part will be our minus summation of dni ln ni by gi. Okay. So what we have seen, that this part is equal to 0 and one part is there. This is summation of dni, but what we have considered, total number is constant, so summation of dni is equal to 0. So this part will also be equal to 0. Ultimately the remaining part is equal to 0. Now considering the first condition, d ln p is equal to 0, my left hand side is equal to 0 here. Okay, so removing this sign, I will get summation of dni ln ni by gi is equal to 0. This is first equation. Then I will consider the second one, alpha dni is equal to 0, mark it 2. Then beta summation of ei dni is equal to 0, mark it 3. So combining these three, what I will get, summation of ln ni by gi plus alpha plus beta ei dni is equal to 0. I just 1 plus 2 plus 3. I have added these three equations. Okay, so which implies I can write ln ni by gi plus alpha plus beta ei is equal to 0. Okay, so or ln ni by gi is equal to minus alpha plus beta ei. Okay, so if I write or ni by gi is equal to e to the power minus alpha plus beta ei. So ni is equal to gi by e to the power alpha plus beta ei. This is our first Maxwell Boltzmann distribution law. We have derived it. Okay. Then we will derive this same thing again. So I will not write again this Stirling approximation, but I will use it. So by using the Stirling approximation, what I will get first use here. Okay. This, but we will consider one thing again. Since this gi is in general very greater than 1, so I will consider gi minus 1 is almost equal to 1 here. Sorry, gi here. So here I will consider gi and here also I will consider ni plus gi. So let us first write it, and ni plus gi factorial minus summation of ln ni factorial minus summation is there, right? So summation of ln gi factorial. Okay. Then we will use your Stirling approximation formula. Summation, use this part, ni plus gi ln ni plus gi minus ni plus gi. I have used this. Okay. Then for the second one, again minus n summation n ln ni minus summation of ni. This minus will be plus. then minus summation of gi ln gi, minus minus plus again, summation of gi. Okay, so here summation of ni is again total number of particles. When I will differentiate it, this will be equal to 0, this is plus gi, differentiate it, this will be equal to 0. But here you see, instead of differentiating it, this part and this part will be cancelled out automatically. So my part will be, remaining part will be simply summation of ni plus gi ln ni plus gi minus summation of ni ln ni and minus summation of gi ln gi. Okay, so now differentiate it, d ln p, the left hand side. So this part, take again first function into second function. So if you consider this first function, second function as constant, then what you will get, summation of ln ni plus gi, put it as a constant, then differentiate it. So this will be dni plus dgi is equal to 0, so this will be only dni. Okay, plus then keep it constant, ni plus gi, summation ni plus gi, keep it as constant. So this part again, ln ni plus gi part, 1 by x dx, 1 by ni plus gi, ni plus gi into d of this, so dgi is equal to 0, so automatically dni minus this part, again first function into second function, put it constant and summation ln ni into dni, then second part ni, 1 by ni dni, 1 by ni dni minus this part automatically will become equal to 0 because this is constant, so this part will be equal to 0. Now you see, this part will be cancelled out, this will be cancelled out, so ultimately this dni and dni, this will also be cancelled out, so remaining part is only this and this. So if we write once again, then what I will get, summation of dni ln ni plus gi minus summation of dni ln ni. Okay, so rearrange it, summation of ln, this is plus, this is minus, so I can write ni plus gi divided by ni, this part, into dni. Dni is common. Okay, now according to the again condition, this condition, I will put the left hand side is equal to 0, so I can put directly this equal to 0. So since right hand side is a 0, I can reverse it by just simply multiplying both sides by minus. What I can do, I can write summation of ln ni by ni plus gi into dni is equal to 0, because I can multiply both sides by minus, so I will get this. This will help us, that's why we are doing this. Okay, now in this, what I will do, I will add these 2 and 3 equation, same thing. So again, if I write it as 4, then 2 plus 3 plus 4, what I will get, I will get ln ni by ni plus gi plus alpha plus beta ei dni is equal to 0. Okay, so this implies that same thing, similar to that, I'll write ln summation is there, ni by ni plus gi is equal to minus alpha plus beta ei. Okay, so remove the log, it will be exponential again. I will write here ni by ni plus gi is equal to exponential of e to the power minus alpha plus beta ei. Again, just alter this so that this will become plus ni plus gi divided by ni is equal to e to the power alpha plus beta ei. So this will be our 1 plus gi by ni is equal to e to the power alpha plus beta ei. So gi by ni is equal to e to the power alpha plus beta ei minus 1. So ni is equal to gi by e to the power alpha plus beta ei minus 1. This is our Bose-Einstein distribution law. Okay, so we have derived here the Maxwell Boltzmann statistics distribution law, and here we have derived the Bose-Einstein distribution law. Let us now move towards Fermi-Dirac distribution law. Same thing, we are doing the same thing, nothing else. Again, you use the Stirling approximation here. So if we use the Stirling approximation here, I will get gi summation of gi ln gi minus gi, okay, minus summation nn ln ni minus plus summation of ni, okay, minus summation of gi minus ni ln gi minus ni ln gi minus ni plus minus plus gi minus ni. Okay, so if something is cancelled out, look at that. This is ni minus gi, this plus ni minus ni will be cancelled out, plus gi minus gi will be cancelled out. So remaining part is only summation of gi ln gi minus summation of ni ln ni minus gi minus ni ln gi minus ni. Okay, so by using the Stirling approximation, we have removed the factorial sign only, so that we can differentiate it. Okay, so now we differentiate it again. d ln p is equal to summation, this part will be 0, this is a constant part, so here again you consider this part as constant, so minus summation ln ni dni minus summation is already there, so ni 1 by ni dni, so dni by ni minus again this part ln gi minus ni, okay, into this minus will be plus, so I will write here plus, minus will be plus, minus the dgi is equal to 0, minus plus dni plus, again what I will do, this Gi minus Ni is constant. 1 by this part, 1 by Gi minus Ni into dni. Okay, so this part will be again cancelled out. I will get dni part. This part will be cancelled out. I will get dni part. Okay, now what we will see, this dni plus dni and minus dni will be cancelled out again ultimately. So I will get, this is plus, so summation of ln gi minus ni by ni into dni. Okay, again this part is equal to 0, so I will put this is equal to 0. Then again, if you consider this is 5, then I will add 5 plus 2 plus 3, these two equation. I will add this 3 equation, then I will get summation of ln, this part again I will change it by multiplying by minus sign. I will again change it ni by gi minus ni. Okay, plus alpha plus beta ei dni is equal to 0 by adding this 5 plus this part. You can write simply minus of this is equal to also 0, so that I can alter this part. This will help us in doing the calculation. So here what I will do, again I will get, therefore ln ni by gi minus ni is equal to minus alpha plus beta ei. So ni by gi minus ni is equal to e to the power minus alpha plus beta ei. Okay, now reverse this thing, gi minus ni by ni is equal to e to the power minus alpha plus beta ei. So gi by ni, minus 1 will come here as the plus 1. I will get e to the power minus alpha plus beta ei plus 1. Okay, so again reverse it. Okay, I will do here. Ni by gi is equal to 1 by e to the power alpha plus beta ei plus 1. This minus will become plus and plus 1 is already there. Okay, so ni is equal to gi by e to the power alpha plus beta ei plus 1. So this is our Fermi-Dirac distribution law. So we have got Fermi-Dirac distribution law, Bose-Einstein distribution law, and this Maxwell Boltzmann distribution law. Now the thing is, if you see the pattern, look at the pattern of these three, then you will see that here the only difference is here one term is minus 1 and here one term is plus 1. Okay, this part, in all this case, this ni by gi, the physical importance is important. This part is called your occupation index. Occupation index. When this part ni by gi, this occupation index is very less than 1, then this part e to the power alpha plus beta ei part will be very greater than 1. When this part is very less than 1, then it is very greater than 1. And this happens at very high temperature and very low particle density. Under this condition, if you see that if you remove this part and this part, then all these both distribution laws become the single one, Maxwell Boltzmann statistics. Or at very high temperature or low particle density, we can say that the quantum statistics becomes the classical statistics or moves towards the classical statistics. So it means, what does it mean? This occupation index is less, very less than 1 means only a very small fraction of total number of phase cells are occupied and rest are empty in that case. Okay, in that case you will move towards, you will merge all these to that Maxwell Boltzmann statistics, this Fermi Dirac statistics, and this will move towards this. Okay, so I hope all of you have understood these things, and if you like it, then please comment me so that I can make the other videos. Thank you.